Alright, so today we are talking about the chi-squared test for independent variables. Again, that's pronounced chi-squared or chi-squared, not x-squared. So the purpose of this test is to take two variables that we're graphing on our x and y axis and determine whether or not those variables are independent, as opposed to saying that y depends on x. So this formula right here is what we're going to use to determine this, as well as using a table to kind of compare our value to. The difference between observed frequency and expected frequency is as follows. So observed frequency is literally the numbers in the table. The expected frequency is based on the probability of an event occurring. This is basically the same thing as calculating your expected value, which means we're going to take the probability of the event happening and multiplying it by the number of times, or the total number of things in that spot, or the observed frequency. The next thing to talk about is the degrees of freedom. Basically, this is just talking about the size of the table, or the number of data points that we have. So the more data points we have, the higher the chi-squared value will be, which means that the target number we're looking for to determine independence grows as we get more data points. To find the degrees of freedom, you take the number of rows minus 1 times the number of columns minus 1 in the table. So if you have a table that's 2 by 2, your degrees of freedom would be 1, because you're basically just taking 2 minus 1 times 2 minus 1. Another table that was 4 by 3 would have a 6 degrees of freedom. Again, this has to do with how we arrange, how much flexibility we have in arranging the data in the table. And then finally, this table right here is going to explain to us, or basically it's going to provide us with our target numbers depending on how confident we want to be in our number. So you notice at 10% confidence, we have smaller values than at 1% confidence. So how does this work? Well, the first thing that we're going to need to do is calculate our degrees of freedom. So when we're doing that, this table is 2 down by 3 across. So if I take the number of rows, the number of columns, I just get 2. So I'm going to be using 2 degrees of freedom. So when I reference the table on the previous page, I'm using the row with the 2. What we're also going to want to do is get the total of each row and column so that we know how many data points we're dealing with. So if I add up my numbers, I should get 253 here, 292 here, 304 over here, 311 over here, 538 over here, and then if I add going down and I add going across, both of those numbers should equal 849. Alright, so we have our observed frequencies and the total of each row and column. The thing we need now is our expected frequencies. So like I said, we're basically using our probability to calculate expected value. So if you remember, for independent events, the probability of A and B happening at the same time is the probability of A times the probability of B. So if these our independent events, the expected values we get in our table will match or be very close to the observed frequencies. So let's see what happens. In order to calculate the probabilities, I'm going to need my 6 data points. So we're still going to have A and B. Still going to have 18 to 35, 36 to 59, and 60 plus. To calculate the probability, again, it's the total number of ways something can happen divided by the total number of terms in the table. So if I was calculating the probability that I got a person who is 18 to 35 and in party A, I would take the probability that I'm 18 to 35 times the probability that I'm in party A. And for expected value, we said it's probability times the total, which cancels one of these. So basically, the shortcut is to find the expected value for the block that I've got highlighted. I want to take the total here times the total here and divide by the overall total. So if I take 253 times 311 and then divide it by 849, I should get about 92.7. And then I want to repeat that process with all of the other combinations of row and column. So for example, to get the one underneath it, I would take my 253 times 538, and that would give me the block for B to 18 to 35. So that would be 160.3. Can do the same thing over here. Same thing over here. Same thing over here. And same thing over here. And if I did it correctly, the totals of this table should be exactly the same as the totals of the previous table. So if I add 92.7 and 160.3, that should give me 253. If I add my 36 to 59 column, it should give me 292. 304 goes here. 311 goes here. 538 goes here. And then finally 849. So since all of that matches up, I can be pretty confident that I did everything correctly. Alright, so that's our expected value table. If we remember from the previous page, the formula for calculating your chi-squared is that we're going to take the sum of observed minus expected squared and divide that by the expected frequency. So what you're going to do is take those grids, those tables, and convert them into two lists. So I'm just going to take the values from the table, make them into a single XY table, just like we do on our calculators. So the way that I'm going to do this, I'm just going to make them go across, but you can kind of organize them however you want. So I would have 85, 95, 131, 168, 197, and 173. And then for the other one, I will use the values from my expected value table. Going in the same direction that I did when I wrote these out. So going across. $160.3, 185.04, and then 192.6. Alright, and so finally, from here, we should be kind of familiar with the steps because they are the same as what we would do for our standard deviation. So we'll create a list using our calculator for FO minus FE. Create another list for FO minus FE squared. And then create another list where you divide FO, or basically divide the previous list by FE. And then use your calculator again to get the total. So if you do that, you should get this. So if I compare that back to the previous table, I had 2 degrees of freedom. And the problem that we just worked specifically said to use a 5% level. So this will always be given to us, or if it's not given, we will have to just sort of decide whether we want to use 10%, 5%, or 1%. So if I'm at 5%, I'm comparing this value to 5.99. So if these were independent, the chi-squared test would give me a value less than 5.99. So, for our sort of last step, 8.56 is greater than 5.99. So they are not independent variables. All right, that's all there is to it. I know it's a lot of steps, but with a little practice, we'll have it down. I will see you guys in class.